Hello everyone. In this video we are going to talk about a topic called blocks in contact with each other. This is not a difficult topic or concept, but it's something that we haven't run into yet before. So we need to look at that in case we ever see a block in contact with each other. So I'm actually on homework 5 and I'm going to do problem number 1 with you as my example. So in problem 1 we have 3 blocks. It says that their masses are 5 kilograms, 6 kilograms, and 4 kilograms respectively. And a force of 80 newtons is applied to block 1. So we're basically going to have a person push on this set of connected blocks, or blocks in contact, with a force of 80 newtons. All right, so let's start with the phrase blocks in contact. What does that mean? So we just got done looking at pictures that might have been like this, like a 5 block, a 6 block, and a 4 block. And they might have been connected by a string. And then maybe we pulled the whole thing with a force of like 80 newtons. And we found out that there was tension in the string. We'll call it FT1 and we'll call this FT2. There were different tensions in each of the strings. And if I was pulling with an 80, then the tension in this string would have been 80. So there also is a force pressing down. We'll call that FW. There's a force pressing up. We'll call that FN. And then there was tension in the strings between the blocks. So this is kind of the same thing, but this time there's not string connecting the blocks. The blocks are actually touching each other. So the phrase blocks in contact is when blocks touch each other. So just like before, there's going to be an FW pointing down, there's going to be an FN pointing up, but here's the new piece. There's going to be a force that this 5 presses on the 6. I'll draw it like this. And then there's going to be a force that the 6 presses back on the 5 that's going to be equal and opposite, because that's like Newton's third law. And this is what we're looking for. So before we were looking for the tension in the string, now we are looking for the forces that each block pushes back on the other one. So like the 6 block pushes on the 4, and then the 4 block pushes back on the 6. So this is the question mark of what we're solving for, and this is a question mark of what we're solving for. Okay, so the approach to this is going to be the same as we did when we had blocks connected by strings. So before we can find the forces that the blocks in contact exert on each other, we have to find the acceleration of the system. So I'm going to write down F net equals M net times A, and I'm looking for the A. All right, the F net is going to be what makes the system move minus any frictions. So in this problem, it's a frictionless surface, so I don't have any friction. But if I had friction, I'd have to draw in the little frictions down here, and I'd have to subtract them off. So we have a force of 80 that's making it move, and minus any frictions, and we don't have any frictions, so we get to keep going. And the total mass would be 1015. And so then we can find the acceleration of the system is 5.33 meters per second squared. All right, and then once I have the acceleration of the system, now I can tackle the forces that are happening between each of those blocks. And to do that, I have to draw a free body diagram of each individual block. I like to make my free body diagrams kind of like line up. Like I'm going to do the 4 underneath, the 6 underneath, and the 5 underneath. So I'm going to start by getting myself ready to do that. So I'm going to draw my pictures over here. So here's my 4. We'll put our 6 over here. We'll make it a little bit taller. And then we'll use the 5 over here. All right, and the secret to these problems is to start as far away from what you know. So we know the 80. So I'm going to start with the 4. So I'm going to come down here. All right, so if I had to turn the 4 block into a dot, here's its dot. We know that there's FW. That would be 39.2. FN is 39.2, but we really don't care about that. We care about what's happening in the X direction because that's what is going to give us our net force. So let's write down what we know. We know the mass is 4. We know the acceleration is 5.33. And what is the net force? So back when we had things up here, we had like the string and we had the string over here. But now all we have is that this 6 block pushes on the 4 and the 4 pushes back on the 6. But we're only talking about the 4 block. What is pushing on the 4? What is pushing on the 4 is right here, the 6 block, and it's pushing the 4 to the right. So if I was using this free body diagram and turning it into a dot, it would go like this, and we would label that the force of the 6 on the 4 block. This is the force that the 6 kilogram block applies on the 4 block. So that kind of makes sense. If I had friction, I would draw that backwards, but I don't have any friction. And you can see then that's the only force in the picture. So that has to be the net force. So I'm going to write that 6 on 4 here. And I'm going to solve for that. And that turns out to be 21.32 newtons. So I'm going to circle that. And then I'm going to go back up to my picture here and clarify this for myself. So the 6 block pushes on the 4 with 21.34 newtons. But according to Newton's third law, the 4 block pushes back on the 6 with the identical force of 21.34. So I'm going to leave that there. And then I'm going to move over to the 6 block, and I'm going to turn it into a dot. And we just said that the 4 presses back on the 6. So the 4 presses to the left. The 4 presses to the left at 21.34. But when I look at my picture here, I can also see that the 6 presses on the 5 and the 5 presses on the 6. I'm talking about the 6 block. I only care what is pressing on the 6 block. There's a 5 pressing on the 6 block, and that force is going to be longer, and the reason I know it's going to be longer is I expect the whole system to be going to the right. So I'm going to call this the force that the 5 block presses on the 6 block. And then I'm going to do my F net equals MA. And let's do again the easy part. We know that the mass is 6. We know that the acceleration is 5.33. And my F net will be the big arrow minus the little arrow. So this is going to be the force of the 5 on the 6 minus 21.34. And we find out that the force of the 5 on the 6 is 53.3 newtons. So I'll circle that. But then I like to go back up, and I like to put that back in my picture up here. So the 5 pressed on the 6 with 53.3. That means that the 6 presses back on the 5 at 53.3. And so now I'm at my last block. You might already notice that I really have all of the answers that the problem asked me to solve. So when I do this last block, I'm really doing it to check my answers. And if this one works out, then it tells me that I know that everything's probably correct. All right, so what's happening to the 5? So we turn the 5 block into a dot. And I see I got this hand pressing on it to the right at 80, and I'm going to make this arrow kind of long because that's the way I'm going to call it an FA to 80, because that's the way the system's going. But the 6 is pressing on the 5 to the left. So the this is going to be the force of the 6 on the 5, and that is 53.3. And I'm going to keep writing in a different color down here so we can see it a little bit better. So now I'm going to have F net equals MA. This is a 5. This is 5.33. And we would have 80 minus 53.3. So whatever that equals should equal this. And if they match, then we know that all of our answers are probably correct. So when we look at the next problem, it's going to be like the same process, but it's going to involve friction, which is just going to make our pictures a little bit more complicated. So go through this one a couple of times till you feel comfortable with it, and then we'll be ready to move on to part 2.